Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book, An Invitation to Combinatorics. The topic of this lecture is basic vocabulary of graphs. In this lecture, I'm not going to prove anything. There's really no content. I'm just going to give you some examples of basic graph vocabulary in combinatorics. So let's get started. And let me just tell you what we're going to do in what are the vocabulary that we're going to talk about. We're going to talk about what multisets are, what simple graphs are, what vertices and edges are, multigraphs and general graphs, order, adjacency, incidence, and degree, path, cycles, complete graphs, bipartite graphs. We will talk about those, and subgraphs and graph isomorphisms. Basically, I will go through these definitions and give you examples. So, first of all, if n is a positive integer, then bracket n inside a bracket, is going to be the set 1 through n. And this will be used throughout all over the place. And this is going to be our prototypical set with n elements. It's not so much that we care what the elements of this set are, is that they have n elements. But bracket n will denote that. And bracket 0, for convenience, will be the empty set. Okay. Now, the first thing I'm going to tell you is what a multiset is. Multiset is like a set, except that members need not be distinct. When you said you have a set with whose elements are Jeff, Frank, and Pedram, then you just can't have two Jeffs in that set. You can't put in the set Jeff, Pedram, and whatever else I said. In a set, members are distinct. But in a multiset, we relax that condition, and we can have repeated elements. To say it more precisely, a multiset is actually a set together with a function that assigns to each member of the set a number, a positive integer, or actually infinity, and we think of that as the repetition number or multiplicity of that element. So, for example, you might have the multiset A, B, C, D, D, which often we write as 3 A's, 1 B, 2 C's, and 2 D's. This is a multiset. Its members are A, B, and C, and D, but they have repetition numbers 3, 1, 2, 2, respectively. So, for example, that means that A is repeated 3 times. And again, sometimes we want a repetition number of infinity. If X is a finite set, then the absolute value notation, I won't say absolute value of X, but how I will read that is the size of X. That denotes the number of elements of X. So if we're talking about a set, absolute value does not mean this usual absolute value thing. It means the number of elements in the set. If X is a finite multiset as opposed to a set, then X is the sum of its repetition numbers. So, for example, if I have the multiset A, B, 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 C, 2 A's, 3 B's, and 1 C, then the size of M is 6. M has 6 elements in it. 2 of them are A's, 3 of them are B's, and 1 of them is C's. If A is the set 1, 4, 7, then of course its size is 3. Okay, so let's start with simple graphs. A graph is basically, intuitively, is just a bunch of vertices, a bunch of dots, and some of those dots are connected to some of the other dots via edges. Those connections are called edges. So, for example, in the example that I have here, 1 and 2 are connected with an edge, but 1 and 3 are not. And I have 10 vertices and 15 edges. Each edge of a graph just connects 2 vertices, and so you can represent it as a pair of vertices. So, for example, there's an edge between 2 and 7, and we refer to as the set 2, 7 in this kind of a graph. So, more formally, a simple graph is a pair of vertices, a pair of sets V and E. V is the set of vertices, and it has to be non-empty. You have to have at least one vertex to have a simple graph. And E is a set of edges, but it could be empty. And the set of edges is each element of E is actually a subset of size 2 of V, because each element of E is telling you which vertex is adjacent to each other vertex via an edge. So, for example, I might define for you a graph, a simple graph, by giving you the set V and the set E. The set V here is 1, 2, 3, 4. So this graph has 4 vertices, and the edges are these 4 pairs of vertices, 1, 2, 2, 3, 3, 4, 1, 4. This would be a definition of a graph. However, we like to often, if we can, to draw a picture of the graph. And this graph, you could draw it in any one of these ways and many other ways. All of these have 4 vertices, 4 nodes. Those are one for each of the elements of V. And then for each element of E, the edges, which are a pair of vertices, we just draw an edge between those two things. And how we draw them doesn't really matter. What just matters is that information is the first set and then the second set that tells us what's connected to what. In an area of mathematics called topological graph theory, how you draw things matters quite a bit. But in combinatorial graph theory, how you draw a graph does not really matter. All that matters is we have a bunch of nodes and some are connected to others. It's such a versatile object that can be used to model many different things, and sort of it's good to have some vocabulary going with it. Now, for a simple graph G, the one that we just defined, V is a set, the vertices are a set, and E is a set of subsets of size 2. It's a set. However, if we allow E to be a multiset, what does that mean? That means that I'm allowing one pair of vertices to appear more than once. That means I'm allowing repeated edges. Then the object that we get is called a multigraph. Or if you don't want to remember multigraph, you say graph with repeated edges. If we also allow in E a pairs of non-distinct elements. So in E, the elements were just a pair of 2 elements of V. But if we allow that element of E to be a multiset, be like 1, 1, which would be the same as saying that we have a loop, then what we are doing is allowing loops. And such an object where we have loops and repeated edges is called a general graph. Some people call it a pseudograph, or you might just call it a graph with repeated edges and loops. So a simple graph does not have repeated edges. It doesn't have loops. If you have repeated edges, then you call it a multigraph. If you have repeated edges and loops, then you call it a general graph. Okay, so some basic ways of talking about this vocabulary. So if you have a general graph, so V's set of vertices is the set of edges, we're allowing both loops and repeated edges. The number of vertices, the size of V, is called the order of G. So the order of a graph is the number of vertices. If alpha, the pair XY, is an edge, then the way we talk about that is that we say alpha joins X and Y. We say X and Y are adjacent, or we say X and alpha, the vertex and the edge, are incident. So incident is about a vertex being on an edge. Adjacency is about 2 vertices. 2 vertices are adjacent because they have an edge between them. And we use the vocabulary, we sometimes say alpha joins this vertex to that vertex. We also say that X and Y are vertices or ends of alpha. Okay. The degree of a vertex. So again, in a general graph, if you have a vertex X, then the number of edges incident with X. So that means the number of edges that are coming out of X. That means the number of edges that X is one of their vertices. That's called the degree or valence of X. But one thing to notice that for a general graph, that a loop at vertex X contributes 2 to the degree of X, because it's sort of, you think of it as going out and coming back in. So you count it as twice. So as an example, here's the general graph. It has 3 vertices. Its order of G is 3. The size of V is 3. Degree of 1, the degree of the vertex 1 is 4. There's 4 edges. I mean, there's 1 loop that counts twice, and then 2 other edges coming out of it. Degree of 2 is 3, and degree of 3 is 1. 3 is adjacent to 2, but it's not adjacent to 1. I'm just talking about this graph so that you become familiar with the vocabulary. The vertex 3 is incident with the edge 2, 3. Now notice that in a general graph, I can't really actually, if I want to be formal about it, talk about edges as pairs of vertices, because if I say the edge 1, 2, then it's clear that I'm talking about one of the edges connecting 1 and 2, but it's not clear which one. So for general graphs, if you want to be formal about it, you need to give names to the edges as well as to the vertices. but I'm not going to do that. So now I'm going to talk about special classes of graphs, graphs that come up so often that they have their own names. And so these are examples of graphs. In fact, all of them are going to be simple graphs, no loops or double edges, but they have special names of their own. The first one is paths. So a path is just a string of vertices connected with edges. So in this path, for example, I have 1, 2, 3, 4, 5, 6, 7 vertices, but I have 6 edges, and I call that P6. It's a path of length 6. So the number of edges is the one that gives the name. This is not standard. It is sort of used to be standard, but some people misuse it and might call this P7 because they want to focus on the vertices. So you have to be sort of slightly careful whether or not P6 means a path with 6 vertices or 6 edges. For me, it means a path of with 7 vertices and 6 edges. And I call that a path of length 6. So the vertices are, for example, could be 1 through 7, and then the edges are 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, and 6, 7. So this would be the formal definition of a path, would be where you have vertices and then the edges are these sort of consecutive pairs. Cycles. That's another kind of graph that has its own name. So what's a cycle? Here I've given you 3 examples of them. A cycle of length n. Length is usually talks about the number of edges, has n vertices and n edges. So C3 has 3 vertices, 3 edges. C4 has 4 vertices and 4 edges, and C5 has 5 vertices and 5 edges. That's not enough to tell you what a cycle is. Each vertex has degree 2. So for each vertex, there's something going out and something coming out. And also the graph is connected, is made up of one piece. You can go from one vertex to any other vertex via the edges. So this first graph here is C3. This one is C4. This one is C5. And visually, you know what the cycle is. You just go around the circle and come back. And the number of vertices or the number of edges is the length of it. Again, length in graph theory often is referring to the number of edges. In this case, the number of edges and the number of vertices is the same. And we denote this graph of length n, the cycle of length n, with Cn, C for cycle. Okay, complete graphs. So what's a complete graph? The complete graph of order n, first of all, its notation is Kn. K sub n stands for the complete graph of order n. When I say order n, that means it has n vertices. So what is it? It's a simple graph, doesn't have any double edges, and it doesn't have any loops, has n vertices and all the possible edges. All the possible edges as far as you can keep it a simple graph. So you connect every vertex to every other vertex via an edge. So each vertex has degree n minus 1 because it's connected to everybody else. And what's the number of edges? Well, the number of edges, you can think of it as the first one, the first vertex is connected to n minus 1 vertices. The second one is connected to n minus 2 vertices. Finally, the n minus 2 new vertices. It's also you already counted the one edge that went to the first vertex. And then all the way down to the last, the one before last is just connected to one more vertex. And when you get to the absolute last vertex, you've already counted all its edges. And n minus 1 plus n minus 2 all the way till 1 is n times n minus 1 over 2. One way to count that is to notice that the first and the last add up to n, the second and the one before that add up to n, and so you have n minus 1 n's. Well, n minus 1 over 2 n's. And therefore the sum is n times n minus 1 over 2. You could count the number of edges in a different way. You could say that every vertex is connected to n minus 1 vertices, so that's n times n minus 1, but I counted every edge twice, so I double counted, so I have to take n times n minus 1 divided by 2. You can think of that as a proof of the fact that this sum is equal to n times n minus 1 over 2. In any case, a complete graph has n vertices and n times n minus 1 over 2 edges, and every vertex is adjacent to every other vertex. So here's, for example, an example of K6. There's K4, K3, K2, K1 is just a single vertex, K2 is just one edge, K3 is a triangle, and so forth. Okay, now complete bipartite graphs. What are those? So you start with a set of m vertices, L, think of that as left, and R a set of n vertices, and then you connect and put an edge between every vertex in L and every vertex in R. And you do not put any edges in L or in R. So for example, here, K33, you have 3 vertices here and 3 vertices there, and you have connected every vertex on the left to every vertex on the right, but there's no edges on the right, and there's no edges in the left. This graph is called the complete bipartite graph on M and N vertices. M vertices, M vertices, N vertices, and it's complete in the sense that there's an edge between every 2 vertices on the left and on the right. And it's denoted by KMN. So KM was the complete graph on M vertices. KMN is the complete bipartite graph on M and N vertices. Now, how many vertices it has? It has M plus N, because there's M on the right, left, and N on the right. And how many edges? Well, every one of the vertices on the left is connected to N vertices, and there's M of them, so MN edges. Okay, so that's a complete bipartite graph, and that begs the question, well, what's a bipartite graph that's not complete? So a bipartite graph is a graph where no matter how it's drawn, you can partition the vertices into 2 sets, X and Y, and all the edges have one end in X and one end in Y. So they go from X to Y, and there's no edges in X and no edges in Y. If E is the set of edges of a bipartite graph, often we write it as G equals X, E, Y. E is the edges, that's in the middle. X are the vertices on one side, and Y is the vertices on the other. Now, the graph might not be drawn that way, but X and Y are the 2 parts where, and all the edges E go from X to Y. So now what's the relationship between a bipartite graph and KMN, the complete bipartite graph? Well, a bipartite graph is actually just KMM after deleting some of the edges. So you might want to start with K35, and then if you take some of the edges out, then you get a bipartite graph. So the bipartite graph, as opposed to a complete bipartite graph, is just missing some edges. Okay, so for example, let's look at an example. Is C6, the cycle of length 6, cycle with 6 vertices, 6 edges, is that a bipartite graph? Well, I haven't drawn it in the way that shows that it's a bipartite graph, but that doesn't mean anything. So the question really is that, can I partition the vertices appropriately? What does appropriately mean? It means that, can I put the vertices in 2 different groups so that all the edges go from one to the other, and there's no edges here and there's no edges there? And the answer is yes, you can do that. I'll let X be the red vertices and Y be the blue vertices. And if I do that, then you see that there's no edge between any of the red vertices, and there's no edge between any of the 2 blue vertices. Every edge goes from a red vertex to a blue vertex, and that makes this a bipartite graph. So C6 is a bipartite graph. C5, on the other hand, you might try that on their own, is not a bipartite graph. Okay, so 2 very quick notions. Subgraphs. If I have 2 graphs, G, its vertices are V, its edges are E. Whenever I'm talking about a graph, I'll say G equals parentheses VE. V is the vertices, E is the edges. And H is another graph, and its vertices are V prime, and its edges are E prime. Then H is a subgraph of G if V prime is a subset of V and E prime is a subset of E. So H is a graph, but all of its vertices and all of its edges are already in G. G might have extra vertices and extra edges, but if H lives within G, then we call that a subgraph of G. So, for example, let's look at our C6 again, and let's look at our complete graph on 3 and 4 elements. So is C6 a subgraph of K34? Well, I mean, C6 has 6 vertices, K34 has 7 vertices. So they're not the same graph, of course, but is C6 a subgraph of K34? Well, to see that, we have to see whether or not C6 lives within K34. Well, K34 has too many vertices, so maybe we need to take one vertex out. When you take a vertex out, you can't have its edges just hanging out there with no vertex. You've got to take the edges out too. So I take those edges of that one vertex out, and now I'm actually having K33. Now, this is still not quite C6. This has too many edges. I need to take some of the other edges out. But if I take those 3 edges out, now I have a graph which I got from K34 by eliminating a vertex and all its edges, and then eliminating some other edges. And this graph is actually the same as C6. If you color the vertices like this, you see that you're going from a red to a blue to a red to a blue to a red to a blue back to the red. You actually have a cycle of length 6. So C6 is a subgraph of K34. If you label them appropriately, then the vertices of C6 are sitting inside K34, as are its edges. To be more precise, what I should have said is that K34 has a subgraph that's isomorphic to C6. That's sort of basically the same as C6. And that's the next thing that I want to tell you. If you have two graphs, when do I think of them as being actually the same graph? Like in the previous example, the graph on the left, C6, is the same as the subgraph of K34 that I drew there, but they're not drawn quite exactly the same way. On the right, I've drawn it as a bipartite graph, and on the left, I didn't. So we want to think of those two graphs are the same because they have basically the same vertices and the same edges, and that's what we call isomorphism. So if you have two graphs, then we say that G is isomorphic to H. When do we say that? When we're allowed to say that? The way we're thinking of it is that when we say isomorphic, we mean the same as far as combinatorial graph theory is concerned. If there is a one-to-one onto map from the vertices of G to the vertices of H, V of G I'm using to denote the vertices of G, and V of H I'm denoting to the vertices of H. So you need a function that takes a vertex of G and gives you a vertex of H. And that map function has to be one-to-one and onto. That means that every vertex of G has to go to one specific vertex of H, and every vertex of H has to come from one vertex of G. But that's not enough. It also has to be the case that if you have an edge of G, then f of x, f of y is also an edge of H, and vice versa. If you have an edge of H and see where they came from, it should have come from the edges of G. So the vertices correspond. There's a one-to-one correspondence between the vertices, but that correspondence preserves the edges. Every edge goes to an edge, and vice versa. Every edge comes from an edge. If this map F then is called an isomorphism between G and H, and the way we think of it again is that the two graphs are the same. So, for example, is C4 and K22 isomorphic? Well, what I have to do is to have to give you a function, tell you this vertex corresponds to which vertex. So, this first vertex, the lower left vertex in C4, I'm going to call 1, and I'm going to send that, the map is going to send it to this lower left elements of K22. And then the second one, I'm also going to send there. So far, so good. 1 went to 1, 2 went to 2, and between 1 and 2, there was an edge in C4. Between 1 and 2, there was an edge in K22 again. Now, I'm going to call the third vertex here 3, but I'm going to send that to not the right-hand vertex on top in K22, but on the left one. And the reason is that 2, 3 is an edge, and I want 2, 3 to be an edge here as well. And finally, the fourth vertex goes to 4, and I have a one-to-one onto map from the vertices to vertices. I've told you which vertex here goes to which vertex, but the more important thing is that the edges correspond. So here 3, 4 is an edge, there is a 3, 4 is an edge. Here 2, 4 is not an edge, and there 2, 4 is not an edge. On the other hand, 4, 1 is an edge on both of them. So both of these graphs are the graphs whose vertices are 1, 2, 3, 4, and the edges are 1, 2, 2, 3, 3, 4, and 4, 1. And therefore, the answer is yes, these two graphs are isomorphic. And again, isomorphic graphs are considered the same in combinatorial graph theory. And this was the end of this vocabulary lesson. I will see you in future lectures.